Okay. And we are live again. Okay. That's good. So, welcome back to the second half of the lecture. Let me check if all systems are going. Yeah. Recording, streaming, I see myself. Super. Okay. Where did we stop? We stopped at where we determined what are the global errors in the method, and we know what they now are, order of magnitude. So that means that we know that if we take a smaller step size, that it will get better. But now we want to do an estimate of the global error. So in practice, we need to estimate this global error. Error, capital E. And how do we do that? Well, let's first start with the intuitive way. So let's suppose you take some step size h, and then with that step size you determine what the solution is. And I put a hat on that because it is an estimate of the solution. And let's say the estimate of that solution is 3.156728. That is the number you calculate. Now, you're not sure, so what you do, you refine your step size. You divide it by 2, and so you take twice as many steps, and then you calculate what the solution is. And let's call this h, and let's call this h over 2. Meaning, it's of course all at the end time in both solutions, but it's to indicate that I now use a smaller step size. And then suppose you find as an answer 3.149152. Now, my intuitive way would be to say, well, the real solution, so the real solution of this y at t is then probably, well, the 3, I see both a 3, so that's probably 3. Then I see both a 1, so that's probably okay. I see 5, 6, so that could be 6. I see 4, 9, so my guess is it's 5. And that's it. More digits I do not trust, right? So that is a way how we estimate. But the big thing is that we do a step and then we refine our step and then we look at the differences. And that's exactly, there's a systematic way to do that. And the systematic way goes like this. We say that the solution at that time t is, so that's the real solution, it's the approximate solution at that time, plus, some, it has to do with something, with a step size to some power and a constant. So, and then for Euler, of course, the global error is, of course, p is then equal 1, and for the Hoyne method, the global error p is 2. So this is the error. So this is the, how do I say, the numeric solution, and this is the true answer, which we don't know, but we want to know what it is approximate, what error are we making. So what we do then, we first integrate with step size h, and then we determine a solution, and let's call that y of h at t, right? And then next we integrate with a step size h over 2, and we call that solution y h over 2 at t. Okay, then we have these two solutions. So what can we say of them? Well, this y h over 2 is, of course, the true answer, plus or minus, because it's an error, so we don't know exactly, plus or minus is c1 times this h to the power p. And the p is fixed. That's for Euler it's 1 and for Hoyne it's 2. But we also have this other solution. Sorry, I made an error, of course. This should be h. This is our original solution. So this should be IYH. This is first with this step size. And then h over 2, I do the same. Well, the true answer is, of course, it's still the same true answer. But now I used a smaller step size. I used h over 2 to the power t. And the C1 is approximately, I guess, should be approximately right. Now I have here two equations and I have two unknowns. Because the unknowns are, of course, the true solution and this C1. I don't know what that is. I don't know how it behaves, but I don't know what the one is. And of course, it's with a certain uncertainty both. Due to the plus or minus, that's a bit of a strange calculation, but I can still make an estimate on the global error. So then the estimate on the global error, global error E, goes like this. From these two, I can determine that this E, in absolute sense, is, which is the true solution, minus, and then I say that's the most accurate one I calculated, that the error in the true solution will be something like this, 1 over 2 to the power p minus 1, that's because and then we take the difference, h over 2 times minus the solution of h. So we look at the difference in the two solutions, then we multiply that with some factor, and it only depends on the method, and that gives us this global error estimate that just follows from this equation. And that's actually what we were doing intuitively. We were looking at these two numbers, and then we were taking the difference, this one, and then in our case we should have multiplied, if it was with the Euler method, if p is 1 and 1 over 2 minus 1 with 1. So for this case, so let me copy and paste this. Can I do that? Yeah, I can do that. So I'm selecting this one, and then I say copy, and I duplicate that here, and blow it up again. So here we are. Now for this case, if I then apply this, then my error estimate would be, well, I use say I use this Euler. I had used Euler method. Then p was 2. P was 1. Sorry. Then I would have 1 over 2 to the power 1 minus 1, which is 1, of course, times, and then I take the difference to these two. So 3.149152 minus 3.15678. Well, this is a 1, so then the error estimate is, I'm not so good at doing 0.00 and then something, right? That's a 6, it's a 7 or something like that. So that would be my error estimate. And then which number? Well, I usually take the most accurate one. So then I would say the accurate solution, or the solution is approximately 3.149 plus or minus 0.007. And that's a nice way to go about. And you see, of course, if you use this method and if you're not happy with this number, then there's of course a solution. If you want a more accurate solution, more accurate solution, what is the way to go? Well, then you just reduce the step size. You just make h smaller. You have to take more steps, but eventually you will get a better result. Okay, so now we know how we can, the different methods, we know how we can estimate what the error is, but as important or even far more important than accuracy is stability. So more accurate than accuracy is stability. Because if you don't have stability, then the whole thing will collapse, of course. And what do I mean with stability? With stability, I mean the propagation of errors. And what does propagation of error means? Well, in one step you made an error, and then you hope that that error, you don't drag that error along, you don't amplify that error, but that the error will slowly go away. And I always try to compare it a little bit with crime and punishment. So let's suppose you did a crime and you're punished for that, then there's a finite time for that. After a number of years you are released out of prison and you can start afresh. And that's also what we want to do in numerical integration. If you made an error, that's okay, but we want that in time the error goes away and that the error does not amplify. So that is stability of the methods. Now let's look at this propagation of errors. We need a test equation. To test the stability of our method. To test the stability of the method. And for the test equation, I like to use the following equation: y dot equals lambda times y. So that is my test equation. Now, why do I like that test equation? Well, it's very simple. It's a simple linear differential equation. And the solutions are also super simple. Solutions are of this form: y of t is some constant times e to the power lambda t. That is the solution. Meaning that if you plot that as a function of time, for if the lambda is positive, then you have these exponential growing things. Lambda is positive. And if the lambda is negative, you have the exponential dying things. So this is lambda negative. So this is like the corona curve at the moment, right? We have an exponential growth in people who are getting sick. And hopefully something in the system will change by which the growth then will do. And change in the system is that we now have the lectures online and everybody is staying at home. So hopefully then we get a different system and then our curve will change. But anyway, we're now in this exponential growth. But is that the only solution of this equation? Is it either growth or exponential decay? And the answer is, of course, no. There are more solutions. And those solutions can be found by using the theorem of a famous guy named Euler. And what does Euler say? Well, if lambda is not only a real number but also an imaginary one, what happens then? Then you get e to the power a plus bi, and now I have to use the Euler formula for that, is e to the power at times e to the power bi. That's still a power calculus. That's e to the power at. And now says Euler, well, this thing, that's the contribution of Euler actually, is cosine bt plus I sine bt. Now you would say, well, we are not doing imaginary mechanics. That's true. But of course there's a constant, and in the end the constants can disappear, but still we can have oscillatory solutions. So not only do we have exponential solutions, but this is an oscillatory thing which goes on like this, blue, 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 blue. And this is of course our non-exponential solution, which is either this or that. And if you then multiply the two, what do you get? Well, you get either, one way is if you take the exponential growth, then we get an oscillation which growth, or we get an oscillation which slowly dies out. So those are all the solutions, and all these type of solutions are in this equation. So for us it's a very good test equation, but because these are the things which we see in mechanics. We see oscillations, we see unstable oscillations, and we see stable ones dying out. And also we see constant solutions. So yes, this is a nice test equation. Now what do we do with the test equation? So again, test equation is y is dot is lambda times y. Then after one step, what happens? So let's just do, we have a solution, so we have a solution, and that's the true value plus some error, right? So this is the approximate error, this is the true one, and this is the error we make. And now we are interested in what happens with the error. And of course, we can take this same equation and put a dot on top. Y dot is just the true dot plus the epsilon dot. Then we put everything into our test equation again. And what do we get? We get y dot plus epsilon dot is equal to lambda times y plus epsilon. And the conclusion is that the error, epsilon dot is lambda times epsilon, it behaves just like the y dot is lambda times y, so like the test equation. So from now on, we focus on this. Apparently this lambda propagates our error, right? So the error propagation, and then we have to distinguish between growing and decaying one. So if the real part of this eigenvalue, if it's positive, then the error propagation is stable, yeah, only on a fixed interval. So meaning that you have growth of this error, exponential growth, but if you just integrate for a fixed amount of time, then you can limit that growth, and then by refining you can limit that error. But it will amplify, it will grow. That is also meaning that your system, it's about the lambda, so your system is also unstable in that sense. So now for the real part of lambda being negative, you have a damped system or a stable system, and that means that you then have an unconditional stable errors propagation. Okay, now back to the method, because we now have a test equation, we now know how this error behaves. So now we're going to go back to our method, and we start now with the Euler. We start with Euler, and yeah, and then we're going to look at this error propagation. So now we have to look at this differential equation, right? So we use epsilon dot is lambda times epsilon, and we're going to use the order method. So what happens? Well, we get en plus 1, epsilon is epsilon n plus h times, yeah, the function value at tn epsilon n, but that function value is of course this function, so that's en plus h times lambda times epsilon n. Or in other words, you could say, oh, the new solution equals, it's all epsilon n here, is 1 plus h times epsilon n. And looking at this equation, you now see that, oh, how does the error behave from one step to the other step? By amplification. So we call this thing, the amplification factor. Amplification factor. So by that factor, my error is amplified. And you would think, oh, it's 1 plus h times lambda. Oh, that's probably a problem, because then it's always larger than 1. But bear with me, the eigenvalues can also be complex. So we not have to look at the real part only, but also at the complex part. So to look at how does this thing grow in absolute sense, we have to look at the absolute value of the amplification factor times the absolute value of the error. So we have to look at this absolute number, right? We give that a name. We call it C, the amplification factor. We say C of h lambda in this case is 1 plus h times lambda. And we want to know in absolute sense, where is this less than 1? Because when it's less than 1, then we don't have propagation of errors. Now lambda, of course, is complex. Or hey, you could say for pure oscillation, if you have a pure oscillation, then the eigenvalues are plus or minus I omega, remember. And if you have damping, damped, or with negative damping and unstable oscillation, you get lambda equals, what was it, minus beta plus or minus I omega, where beta is then the damping. So that is the reason why we have these complex eigenvalues. Or in general terms, we could say, oh, this h times lambda apparently has the form a plus bi, right? Okay, so then we have to look at what 1 plus a plus bi should be less than 1. And if we know where it's less than 1, we first look where is it equal to 1, right? So where is it equal to 1? We look for the boundary, and then we can find, oh, the region within is where it's less than 1, the region outside where it's larger than 1. So how do we find that? Well, we have to work, of course, now with two numbers, so we have to work with a complex plane, right? So how do we do that? We then draw our complex plane like this. And here we have the real axis, the real part. Yeah, the real part of what? Of h times lambda, which is in our case is a. And here we have the imaginary part of h times lambda, which in our case is b. And now for this a and b, these a and b axes, we now have to find out this. Well, if you just put your hand on this part and you look only at a plus bi, you could say, oh, this is like a circle. If the length of that thing is 1, and it's a circle which is shifted to the left. So you could say, oh, this whole boundary is something like this. It's a circle, and then here we have minus 2, here we have minus 1, and then 0 is of course a solution. If you put in all zeros, then oh yeah, 1 is 1, that's okay. If you put a minus 2, you get the absolute value of minus 1 is also 1, and then in between you can you can calculate for yourself, and you will see that this is a circle. And the conclusion is, so this is the boundary, right? So this is where it's equal to 1, and then everything within inside is this stable stuff. Or in other words, that's where the ch lambda in absolute sense is less than 1. And this is all for Euler method. So it is possible, given what the eigenvalue of the system is, it is possible to find a step size h such that you are within this region. However, if you look at the pure oscillatory system, then the eigenvalue is plus or minus I omega, meaning that the eigenvalue is on this axis, and there's no damping or whatsoever. And if you then look at for what step size is it stable, and then the conclusion is only for h is 0, right? Only this point here. The rest doesn't work. So, in other words, if you would integrate a pendulum, this is the solution of a simple pendulum without any damping. So we take a pendulum here in a gravitational field with a mass m, and then you let it go like this, and then the idea is, well, how will it move in time? So let's draw this as time. Then it will swing, and then how will it swing? Well, according to the numerical integration, it will explode, because errors which you made here will propagate, and finally you will get growing solutions. And that's not very satisfactory. We're not so happy with that. I mean, of course, the error is bounded, and if you would reduce your step size, the propagation of the error will be less, but there will still be a propagation, right? So Euler method is not so good for these pure oscillatory systems. So now let's look at Hoyne method. Maybe that's better, right? So what does Hoyne say? Well, we had an epsilon star first. That's the epsilon n plus h times the differential equation, and that was lambda times epsilon n. And then we have epsilon n plus 1, which was this epsilon n plus h over 2 times the differential equation. This thing, first of all, that was this lambda epsilon n plus the lambda the lambda solution which we the approximate solution which we found here. So what is that? Then we have to evaluate at this time, so we have to evaluate lambda times, and then we get again epsilon n, this one, plus h lambda epsilon n. That's our epsilon star n, actually, so lambda. So this is lambda epsilon star n plus 1. Well, then we can, of course, collect terms, so we get epsilon n, plus, what do we get more? We get h times lambda epsilon n, and we get 1/2, that's from this term, 1/2 h squared lambda squared epsilon n. Or again, we can write that as an amplification times epsilon n, and that's 1 plus h lambda plus 1/2 h lambda squared. And so this amplification factor now for Hoyne, and we want, of course, that and again with the h lambda is a plus bi, we want that this 1 plus h lambda plus 1/2 h lambda squared is less than 1. And again, we can plot this. Now it's a bit more complex, of course, doing that in the complex plane, because I don't identify this anymore as a circle. If I write my complex number in here, so I have to write that out like 1 plus h plus bi plus 1/2 h plus bi squared is less than 1. So this is becoming a bit more complex. And if you plot that, those who are very good in complex analysis will immediately see, of course, that this is a ellipsoid. I don't see it, but some do. So here we say the real part of the h lambda, and here we have the imaginary part of h lambda. Then what do we get? Well, apparently, if you take pure real solutions, we again come to the conclusion, oh, that's at -2 is the crossing, and at 0, you can put on all zeros, and then 1 is 1. But now it's a bit oblique, so it's not something like an ellipsoid, something like this. Oh, it should be nice, symmetric. Blah. Something like this, and the top and the bottom are at a square root 2i, and here minus a square root 2i. And again, the area inside is the stable. Now that looks good, but still you do not have, with Hoyne, solutions for pure oscillatory systems. So again, pure oscillatory is still unstable error propagation. And the pure oscillatory was lambda is plus or minus I omega, remember? So we are on this axis. Then we can move on. Is there another scheme? And it turns out that there's a very popular scheme, which is called the RK4, or in other words, a Runge-Kutta-4 method. Shows a nice scheme, shows a nice escape. And also in the book it's mentioned, and you see also pictures of Mr. Runge and Mr. Kutta. And there's a bit of background on them. So how does the Runge-Kutta work? Well, you already see with the 4 that you have to do probably 4 things. And it comes down to this, that you have to calculate a number of slopes. And the first slope you calculate is just the initial slope. And then the second slope you calculate is, well, you take halfway a time step, so you're going to sit halfway, and then you need an approximation of the function halfway. Well, I know an approximation of the function halfway, because then I use this slope, k1. So now I have a nice approximation of the function value halfway, and I calculate what is the slope. Actually, I'm not so happy with it. I want to have a more accurate result. In the spirit of Hoyne, halfway. So again, halfway I calculate everything, But now for the approximate value halfway, I do not take this slope, but I take this slope, of course. So I take h over 2 k2. So now I have this halfway point, which might be a bit more accurate, and then k4 I do again at the end point, and now at the end point I estimate it with k3, which is a sort of a better estimate. Now with these 4 slope values I can now approximate what my new solution is. And my new solution is h over 6 times, and then I take k1, I take 2 times k2, I take 2 times k3, and I take k4. And then I could say plus order. Now what would be the order of this method? Well, the local truncation errors of course I do 4 things, so it's 5, h to the power of 5. So my local truncation error is to the power of 5, and my global one, of course, is of the order h to the power of 4. But far more important, of course, than this error is, of course, the magnification factor. And I'm not going to go into detail of deriving that. I think it's even given in the book, or a reference is given. But if you now plot, look at the stability, the stability. So you look at the C lambda H, and for those who are really interested, it has this form 1 plus H lambda plus H square over 2 H lambda plus H to 3 3 factorial. It's a squared here. Oh, I make an error here. Make an error because this should be plus H lambda squared, and then 1 over 2 plus 1 over 3 factorial H lambda to the power 3 plus da. Well, look in the book. It's a nice polynomial thing, and it's, if you then plot that, and you cannot analytically calculate it anymore, but the real part and the imaginary part of H lambda, then I get a figure like this. It goes like this. I always have to think of a kidney when I do this. I have to redraw it a couple of times, so it should be symmetric, and it's not really symmetric. Something like this. Oh, it should be like a kidney, point 0 here, and then we have this is about 2.8 I, and this is about minus 2.8 I, and this is also minus 2.8. Anyway, this area enclosed, so this is stable. Now I'm really happy. And why am I happy? Because suddenly I have this area, or this axis is within the boundary. So lambda is plus or minus I omega can be within the stable region, meaning that pure oscillatory systems can be integrated in a oscillatory systems can be integrated in a stable manner. So therefore I'm happy. So that is, I think, also one of the reasons why the RK4 is a very popular scheme. Okay, now let's again look at the the global error in practice. And we have seen we have seen that if you refine your step size, that you find more accurate solutions all the way. So if we draw then on this line the step size, and if we plot out here what our global error estimate is, then we can plot our numbers. And we start, of course, with a large step size, so we find some error here. And then we make our step size smaller, we move in this direction, and then we find a number like this, and 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 you would think, oh, if I continue, I can make the error 0, right? If I make smaller steps, then. But what happens suddenly? Then suddenly this happens. So while you are making your step size smaller, your global error is suddenly rising again. And then what is the big question? So why is this happening, right? Well, and of course the reason has to do with round-off errors. Round-off errors. And how does it come? Well, you can represent a number in the computer with a certain finite accuracy. So your epsilon in a computer is I think in MATLAB it's 10 to the minus 14. So if I do in MATLAB 1 plus 10 to the minus 14, and I say, is that equal to 1, then it says probably yes. Because if you add these up, these numbers, then this just disappears, these digits. It can also be 15 or 16, you just have to check that. But that is what we call epsilon. But this epsilon, you make these epsilon errors. And since we use already epsilon, let's call it C2 for now. So if you take many steps, then what will happen? The many steps, the global error for this epsilon is of course the number of steps you take times this C2. And how many steps do you take? Well, you take the n time divided by your step size times C2. And now suddenly we see that the total global error is of course the error which you make in your system, which is a systematic error, CH to the power t, which has to do with Euler or Hoyne or whatever, but also with the round-off error. So this is the method, and this is round-off, and the round-off error is, you could say a C2 over H. Then I now put a T into the C2. But you see that when you make H, so initially when H is large enough, you will not see this error. But when H becomes smaller and smaller and smaller, suddenly this is going to amplify. Or you could say that you can build this graph with two things. One is this method error, so that's this thing which is going down, 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 down. And the other one is the round-off error, which is almost nothing here, but which is exploding here really. And it's the sum of the two, so finally your result is something like this. So, and you probably will not go beyond this, because if you take smaller step sizes here, then your error will explode again. So this is the best you can do. Now I have an illustration for that, and I want to use the last 7 minutes to show that, how that goes in practice. I have to see, what did I want to show? First of all, I want to show a video, because as an example, I want to look at this, at apes. I want to look at, well, in this special type of ape, gibbons, and this is the brachiating of gibbons. So let's have a look at this. This is gibbon brachiating. Oh, I did put the sound out. That's a bit unfortunate. I will put the sound on. Yeah, let's do it again. And it's of course super cool how this gibbon moves about. Yeah. Now let's go back a little bit. Where we see his arms. So what is he doing? He has found energetically a nice way to move about, because every time when he grabs on to the next bar, he does it almost at 0 speed, meaning that there is almost no impact or no energy loss. So you can imagine that such an ape swinging thing with very little energy loss can move about. So you could also look at it as like an inverted way of walking. And actually Mario Gomez was doing research on this when I was visiting at Cornell, and this is his paper, a 5-link 2D brachiating ape model with lifelike energy 0 cost. And the 0 cost is because he so nicely grabs on every time with a 0 speed. So it's like walking but with a 0 impact on the ground, but then inverted. Now what does he do? He makes theoretical models, and of course the first one is just a single pendulum. And the single pendulum swings, and every time when he's here, then he moves his hand to here, and then he swing again and swing again and swing again. Of course, you can also have not only directly a changing and grabbing, but you can also have a free flight, a parabolic free flight, and that's also what he's doing actually. So you have a free flight, and then again you have a circular path, and you can do also kind of crazy things like bzzzt, and you can go around like this, but you can even get it more crazier, that you say, well, it's not a single point mass, it is a rigid body, or it's a two-link model, and even the two-link, where am I? Oh, come back to me, yeah. And even the two-link model can do all kind of crazy motions. Okay, so that's the paper. Now what did Mario had to do? He was doing numerical integration, and for this numerical integration, of course, he has to come up with error estimates. And he follows the book, and he says, oh yeah, I have a global error, and I have a truncation error, a roundoff error, and let's plot it as a function of the step size. And I take a logarithmic plot, but because remember, this is power p and this is power -1. So if I do it on a logarithmic scale, I would find linear with a slope of p and linear with a slope of -1, right? So let's go back to the logarithmic scale. So he plots then for the different methods these error estimates as a function of the step size, and you see initially, like the Euler method, it starts a bit quirky, but then it slowly goes down. And the question is, of course, is the slope of this -1? And yeah, the scales are a bit different, but if you take 2 steps here and then half a step up, it's 1. So 4 steps like this and 1 step up, 4 steps, 1 step. Yeah, so the slope is 1. So it fits with the theory. Why did he stop here? Well, because it was too much work. The computer there was not enough computer power to continue beyond this, because he had to take many steps. Then he moved to a higher order method, so immediately he started to 4th, 5th and 6th order Runge-Kutta. And like here, the 4th order, you can nicely see it's a 1/4, so the slope is 4, beautiful, follows the whole theory. This is still method error, and then here, bang, bang, you see it going up due to the roundoff error. So this is a nice example, theoretical example of how that works with the error estimates. Okay, that having shown, I want to round up with the following thing, that this was, of course, this was the last lecture, the last lecture in Q3. So we continue in Q4. When do we do that? On Tuesday, 21st of April. And then mind you, the lecture hours are from 5:45 to 7:30. These are a bit different lecture hours. And then I will start with lecture number 7, which is closed loop systems. That's just, I follow the book. That's just the same, closed loop systems. So thank you for attending. If you have any questions, don't hesitate to call me or WhatsApp or email. WhatsApp works actually pretty nice, I noticed. And then, one of the questions, of course, is about extra effort and the error and the there's a question here which I already addressed, I think, in the lecture. Are there other things, square root 2, square root 3? Oh, yeah, that could be the case. Well, I have to check that. I could have made an error in my notes during the lecture because it's complex, keeping track of all things, but everything in the book should be correct. Okay, then I'll sign off, and I look forward to see you again in quarter 4.